Hello everyone, this is Dr. Feng Wang again. Let's continue the oxidation reduction reactions of our carbonyl groups. Next, we are going to discuss the stereochemistry of ketones reduction reactions. This is a ketone, and this is the 3D structure I generated with the software we have, Marvin Sketch. You see, this carbon, oxygen, and carbon, they are on the same plane. This is trigonal planar. This is the shape. So if we have a hydride reducing agent, that's going to react with this carbonyl carbon. So because this is a pure planar structure, the hydride can attack from the front side. I consider this is front side, or the hydride can attack from the back side, this side. So this is a molecule that does not have a stereogenic center, but the product, this is a stereogenic center. So the hydrogen, the hydride, the addition product could be from the front side or could be from the back side. That's, this is one of the product, hydride addition product attacked from the front side, or the hydrogen attacked from the back side, from this side, to form the R group. So again, because of the planar structure, so we are going to generate two products. One is S, another one is R. So the opportunity basically from both sides are equal. That's why we have two enantiomers. And these two enantiomers are considered a racemic mixture or racemic. We have other reducing agent. I want to introduce you. The first one is called, this is the structure. It's a diisobutyl aluminum hydride. The second one is called a lithium tri-tertiary butoxy aluminum hydride. Well, the structures I think is a little bit complicated to you, and the names definitely is very long to you. So I don't expect you to remember the exact structure of this reducing agent and this reducing agent, but I really like you to remember at least two names, simple names, DIBAL hydride, basically dibutyl aluminum hydride. This is the lithium tri-tertiary butoxy aluminum hydride. It's a very long name. So the difference between these two reducing agent and the lithium boron hydride, the lithium aluminum hydride, is these two are mild reducing agent. And let's take a look. Well, I will not provide you the details, but you can analyze the structure if you want to. Why they are reducing, they are mild reducing agent than lithium aluminum hydride. Well, a clue to you is basically, how much electrons the hydride bears. The more electrons that you bear, the more reducing ability you have. The less hydrogen, the less electron you bear, the less reducing ability you have. And let's take a look of the reducing reactions with a strong reducing agent, the lithium aluminum hydride, or a mild reducing agent, the lithium tri-tertiary butoxy aluminum hydride. Well, I hope the pronunciation was correct. So if we use a very strong reducing agent, we are going to have alcohol. If we have a mild reducing agent, we are going to have aldehyde, the middle product before we reach the alcohol. So second example here, if we use esters as a substrate, we use a very strong reducing agent. Again, the final product is the alcohol. If we use a diisobutyl aluminum hydride, the milder reducing agent than lithium aluminum hydride, again the product is aldehyde, like the middle product before we reach the final alcohol product. Well, the mechanism is a nucleophilic substitution reaction. The Z group actually is reduced by hydride. In this case, for the acid chloride or esters here, for the aldehyde or ketones, there is a nucleophilic addition reaction. See, this is a substitution reaction because Z is gone. So the final product is alcohol. For strong reducing agent, but for a mild reducing agent, the aldehyde, the middle product, this is the mild aldehyde, because then, if we use a lithium aluminum hydride, very strong reducing agent, we can form the final product alcohol. If not, very strong reducing agent, the reaction will stop here. Acid can also be reduced to alcohol with a strong reducing agent. Amide is a very special case, again, because the amide very strong base. When we do the reducing agent, actually this NH2, this part will not leave this substrate. Instead, only the carbonyl group is attacked by hydride, and reduced this carbon-oxygen bond, totally reduced by a lithium aluminum hydride, a very strong reducing agent. Again, this part will never leave the substrate, so the final product is a hydride. So this is slightly different from acid. In the case of the acid, the OH group basically left this substrate. But for amide, so if we check the pKa values of amide, the conjugate acid, we will see, the amide is very strong base, and it's hard for NH2 to serve as the leaving group. That's why, for this special reducing reaction, the final product is amine. Well, in this table, basically just to summarize many of the reactions, reducing reaction with different reducing agent, the different substrate. I know there are a lot of reactions here. I just explain you some very fundamental things. It would be hard for me to ask you to remember everything in this table. My focus is always, to fully understand the real mechanism of organic reactions. That's a real learning. That's a real education in my view. But again, you are here to learn organic chemistry. You also have a lot of exams to pass for your future career. So, well, again, this table is a very important table. I hope you can, memorize most of the reactions here. I will have many reactions or reducing reaction in the online quiz as well as the homework. So if you want more discussion with me, I would be very happy to do that. Well, let's take a look at oxidation reaction. The oxidation is pretty simple, and we are not going to discuss all the details. So basically, all the oxidation reactions are similar to the alcohol's oxidation reaction we learned, I believe in chapter 11 before. So we can use the chrome or magnate as the very strong oxidative reagent. In acid condition, we can oxidize aldehyde into acid. A second reaction actually is silver oxide plus the ammonium hydroxide to do oxidation reaction of aldehyde only. So there is a name actually for this reaction. It's called a two-lens reaction or two-lens. This is a two-lens reagent. Basically, the two-lens reaction is oxidation reaction of aldehyde only. It's not something else. It's only for aldehyde. It's not for alcohol. It's not for something else. This is a very specific reaction. It's called two-lens reaction. We use silver oxide, ammonium hydroxide as the oxidative reagent to oxidize the aldehyde into acid. And metal silver is formed actually. Silver mirrors, many silver mirrors made from this reaction. Alright, we just finished the reducing and oxidation reactions. The next part of this chapter is about organometallic reagent. So organometallic, reagent, from the name you can guess. That's organic part. Metallic, that's the metal part. This is a generic structure. A carbon, that's organo, and it's the metal. There is a bond between carbon, organic part, and the metal part. We know carbons. This is the electronegativity of a carbon as well as the three metals here. Carbon actually is the highest electronegative atoms in this group of atoms. So which means carbon will pull the two electrons, this bond, two electrons. Carbon will pull the electrons towards itself, or in other words, this carbon bears some negative charge. The metals are willing to give it their electrons to others. So the metal bears the positive charge. So if this is the structure of a three organometallic reagent, so based on the structure and their electronegativity, I think we can analyze the reactivity of the three organometallic reagent. Well, the more negative charge the carbon bears, or in other words, the more willingness of this metal atom to give its electrons towards the carbon, so the more reactive of this negatively charged carbon. That makes sense. So in this three metal atoms, I think of the lithium has the smallest electronegativity. Or in other words, the lithium is the happiest one among these three metals to give its electrons towards the carbon. Or we can say the carbon, lithium molecule here, this carbon bears the most negative charge among the three organometallic molecules, because again the lithium is happy to give its electron towards this carbon. So this I consider the lithium reagent. We call this is the lithium reagent. It's the most reactive in this three organometallic reagent. So the next one is called the magnesium reagent, or we call it a Grignard reagent, because Grignard, that's the chemist who developed this magnesium reagent. The next one is called a copper reagent, or cuprate, organocuprate. So this is the least. This is still reactive, but the least reactive in this three organometallic region. Well, again, I love analyzing the structure. I hope you can analyze, the structures of organic molecules, organic metallic molecules. This helps you to know, to understand the reactions we are going to discuss. Next, well, this is the preparation of different organometallic reagent, the lithium reagent, the magnesium reagent. I remember Dr. Fish used to have an experiment to prepare Grignard magnesium reagent. They are very simple reactions. The cuprate reagent is slightly more complicated than organolithium reagent and a Grignard reagent. We have to use a two-step reaction. First step is the preparation of the lithium reagent, and the lithium reagent react with the copper iodide to form the cuprate reagent. So more organometallic reagent. With this reaction we learned before in OChem 2, I believe the alkynes chapter. So alkyne, this hydrogen shows some acidity. So if we have a very, very strong base, we can prepare organometallic compound. This is called acetylide anion. We can use the lithium reagent to prepare lithium reagent. Lithium acetylide here, they are very strong base. They are very strong nucleophile. Again, this carbon here and this carbon, they bear a lot of negative charge. So they are very happy to share their lone pair of electrons with others. So that makes them a very reactive reagent in a lot of reactions. They can react with the water. So basically, again, this carbon bears a positive charge. It's going to react with the protein. They can react with the alcohol or acid to do, base acid reaction. Again, the lithium, the magnesium, the lithium reagent, they are very strong nucleophile. They are very strong bases. They do acid-base reaction. Well, applications, I think this is a possible application. We can use organometallic molecules to prepare alkanes. Basically, organometallic molecule react with water, so we prepare alkanes. Again, it is one possible application, but I don't think anybody use this reaction to prepare alkanes because of this reagent. They are very expensive. They are very dangerous. So we can prepare alkanes, but alkanes can also be prepared from petroleum, from oil. And I heard the oil is about $20 to $30 a barrel. So it's about the price of water. So that if we can use petroleum oil to prepare alkane, who would like to use lithium reagent, magnesium reagent to prepare alkane? Again, for the education purpose, we still need to know these reactions are possible. Addition reactions of organometallic reactions to a carbonyl compound. This is a very, very important reactions. We use this type of reaction. I would say this is very, very common reactions. Organic chemists use in labs to make all kinds of molecules. So there are many different types organometallic to carbonyl compound. The first one is the first group, the aldehyde and the ketones. So again, this carbon bears a negative charge. It's going to attack this carbonyl carbon because it has some positive charge. Another secret I shared with you, if the carbonyl compound here, this is hydrogen or ketone, alkyl group, the hydrogen and alkyl group, they never leave this group, never leave this substrate. So you can attack to form an oxygen anion here, but they never leave. This part never leaves the substrate. The next step is the protonation of this oxygen anion to form alcohol. So this is the final product of either aldehyde or ketone react with the organometallic compound. Give you some examples. Either aldehyde react with the lithium magnesium region, a lithium region of the lithium. This is another lithium region. The carbon bears a negative charge attack the carbonyl carbon to prepare primary, secondary, or tertiary alcohols. Two-step reaction. First step, nucleophilic attack. The second is the protonation of oxygen anion to form alcohols. Well, I have a quick question here to synthesize a target alcohol molecule. This is the molecule I want to make. It's a secondary alcohol. From the reaction we just learned, this is a secondary alcohol. We have a lithium reagent right side. We have an aldehyde on the left side. We can make a secondary alcohol left side, right side. So when we analyze the structure, we know we can use a magnesium or lithium reagent to do the right side. We can use the left side aldehyde to make again aldehyde to make secondary alcohol. The magnesium reagent to react with the aldehyde to produce the oxygen anion. The second step is the protonation of this oxygen anion to form secondary alcohol. So again, this is a very common organic reactions we do pretty much, if not every day, but very much every week in the lab. Some limitations of this organometallic reagent react with the ketone. Well, this ketone is not a simple ketone. It's a ketone, but also an alcohol. If we just react with this ketone alcohol molecules with the magnesium reagent, we cannot have the product, the magnesium reaction react with the ketone molecule. Instead, it's going to react with alcohol first, because this is strong base. This is a weak acid, but the reactivity of this acid alcohol is much stronger than the carbonyl carbon. So if we want to make this molecule, we do this reaction, we will have product. This would be the final product. So again, the reaction, the acid-base reaction would be much faster than the nucleophilic addition reaction to the carbonyl carbon. So this is a limitation. So organic chemists already developed the techniques to avoid this problem, but that's more advanced organic chemistry thing I will not share with you in this lecture. So now let's take a look at the second group of molecules, ethyl chloride or ester. They react with either magnesium reagent or lithium reagent. So the result is actually Z group nucleophilic substitution will be substituted. will be substituted by the two organo part of either magnesium region or the lithium region, plus the ketone groups, the alcohol, the ketone groups turn to alcohol group. So let's take a look reaction to see, because we need two organo part in the final part. We need at least 2 molar equivalent of either magnesium region or the lithium region to do the reaction. 2 quick examples. This is acid chloride will react with 2 molar magnesium region to form oxygen anion here, then the protonation to form alcohol. You see, 2 molar organo part from this magnesium region, plus the alcohol product is formed. This part, these 2 carbon, this carbon, and this carbon, actually from this acid chloride 2 carbons here. For the esters, the similar thing. This part serves as the leaving group, 2 organo part, methyl added, and alcohol is formed. Let's take a look at why we need 2 molars of organometallic reagent. This is a real mechanism, either acid chloride Z here or ester group here. The first step is the negatively charged carbon here attack this carbonyl carbon to form this oxygen anion, negatively charged oxygen here. Again, the next step, either chloride or this part, the oxalate part, serves as the leaving group. Remember, the second group, the Z, can serve as the leaving group. So because the whole molecule has a negative charge, this molecule is going to try its best to get rid of the negative charge. The way it can get rid of this negative charge here is to form a ketone, to form a new functional group, ketone, carbon-oxygen double bond here. When it does this, the Z group serves as leaving group, forms a ketone molecule. So when this ketone molecule forms, you see the first molar of organo part of this magnesium region actually added to the substrate. The Z group already left. So this is not the end point of this reaction. Again, this carbonyl carbon still bears positive charge, and this carbon here on this organometallic molecule will attack this carbonyl carbon. And when we do the third step reaction, again, this is alkyl group. It will never leave this substrate. Instead, we needed to do the protonation of this oxygen anion to form the alcohol. So, 2-step reaction. The first organo part added here. The second organo part added in this third step. The final protonation to form tertiary alcohol here. That's why for the second group of carbonyl compound, acid, ester or chloride, we need 2 molar organometallic reagent to form tertiary alcohols. The Z chloride or oxalate serves as the leaving group. This is a very simple reaction. Grignard reaction can also react with carbon dioxide to form carboxylic acid. So again, this is another reaction. We can do the reaction, but it's rarely people use this reaction to prepare carboxylic acid, because we have many other ways that we already learned how to prepare organocarboxylic acid. This is just one way to make a carboxylic acid. All right, so it's time to take another break.